So point A is 0, minus 1. So if it is infinite means then we can call it as it is unbounded solution. So put x is equal to 0, 4y is equal to 24, so y is equal to, so these points are connected each other. So this is my feasible region. Hello everyone, welcome back to my new session. I am Shweta, Computer Science Faculty, Vidhyaashram First Grade College, MYSURU. In my last session, I have discussed about LPP by graphical method. So I have discussed so many problems in graphical method. So today I will continue that problems. LPP by graphical method. In my last session, I have discussed about feasible region. So I have discussed the feasible region problems in maximization. So today I will discuss some special cases on graphical method. Let's get started now. So first problem is, I will explain about unbounded solution. So what is this unbounded solution? When LP solution is formatted infinitely large, then we can call it as it is unbounded solution. LP solution is formatted infinitely large. So we'll get the infinity values in unbounded solution. Is a situation where the objective function is infinite. Where the objective function is infinite, that is called as unbounded solution. Where the objective function is infinite, that is called as unbounded solution. Let's see the example for unbounded solution. So we have objective functions and again we have constraints. So what is the first step? So first step is changing this inequality into standard form, that is inequality into equation. So first one we have x1 minus x2 is equal to 1. You just observe these two constraints. In first constraints, it's less than or equal to 1. In second constraints, it's greater than or equal to 3. Here, I have max set is equal to objective function. In my last session, I have discussed about maximization and less than or equal to the constraints. But here, you have mixed constraints. So in this problem, you will get unbounded solution because one constraint is having less than or equal to and another constraint is having greater than or equal to. You just observe this. So this is equation number 1. So first find out, put x1 is equal to 0, minus x2 is equal to 1. So x2 is equal to minus 1. So point A is 0, minus 1. And put x2 is equal to 2. x2 is equal to 2 means x1 is equal to 1. So point B is 1, 0. This is equation number 1 and the second equation is x1 plus x2 is equal to 3. This is equation number 2. So put x1 is equal to 0, then x2 is equal to 3. So point C are 0, 3 and put x2 is equal to 0, then x1 is equal to 3. So point D is 3, 0. So here I got 4 point values. You just mark this value using a graph sheet, x-axis and y-axis. So first see the maximum value out of these points. So maximum value is 3. I will take 0, 1, 2, 3, 4, 5 and 0, 1, 2, 3, 4 and 5 and minus 1, minus 2, minus 3 and minus 1, minus 2, minus 3. Scale is unit is equal to 1 centimeter. So here first see the points 0, minus 1. 0, minus 1. So minus 1 means it is y value. So 0, minus 1. 0, minus 1. And the second point is 1, 0. So mark this 1, 0. This is 1, 1, comma 0. So here you just join these 2 points, and the third point is 0, comma 3, 0, comma 3 and 3, comma 0, 3, comma 0. So I joined all the points. So this is your constraint 1 and constraints 2. So this is your constraint 1. So constraint 1 is x1 minus x2 less than or equal to x1 minus x2 less than or equal to 1, and the second constraint is x1 plus x2 greater than or equal to 3. x1 plus x2 greater than or equal to 3. So if it is greater than or equal to 3 means, so it is outside the region, that is opposite to this region. So it is greater than or equal to 3. Greater than or equal to 3 means it is outside of this region, and less than or equal to 3. So here the first constraint is x1 minus x2 less than or equal to 1. So it is below the constraint. Below the constraint means this part, and above the constraint. So this is greater than or equal to 3. So it is opposite to this region. Opposite to this region means, so this will be the feasible region. So this is the feasible region to this problem. So here we got a special case, because in maximization problem we'll get less than or equal to, but here we have another constraint called greater than or equal to 3. Greater than or equal to means it is outside the region. Outside means it is opposite to this region, above the constraint. So above the constraint means this area is called as feasible area. So what is this? So this area is called as feasible area. So this case is known as unbounded solution. Unbounded solution in the sense is a situation where the objective function is infinite. So it is infinite solution. There is no boundary for this region. So we can call it as it is unbounded region. So in this problem objective function is infinite. So if it is infinite means then we can call it as it is unbounded solution. Unbounded solution, because objective function is infinite. It's above the region means this area is called as feasible region. If your feasible region is infinite means then we can call it as it is an unbounded solution. It is a special cases in graphical method. Sometimes you will get this type of problem also in your examination. So if you get any type of problems you can solve easily. Actually this topic is a scoring topic. Easily you can score in LPP by graphical method. Don't get confused about feasible solution and unbounded solution. If your objective function is infinite means it is a unbounded solution, and if you get a common point and below the region means towards the region means it is a feasible region. So this is about unbounded solution. And the next problem is, so here we have objective function, it is minimization problem. Minimize z is equal to 200x plus 500y. Constraints are greater than or equal to and again less than or equal to. We have two different constraints here. So how to solve this? By graphical method. So what is the first step? Convert this into standard form. So first equation is x plus 2y is equal to 10. Equation number 1. Put x is equal to 0. Then 2y is equal to 10, y is equal to 5. So a is 0, 5 and put y is equal to 0, x is equal to 10. So point B is 10, 0. And the second constraint is 3x plus 4y is equal to 24. So put x is equal to 0, 4y is equal to 24. So y is equal to 6. So point C is 0, 6 and put y is equal to 0, 3x is equal to 24, then x is equal to 8, 8, 0. So these are the point values A, B and C, D. So how to draw this? So here I'll take it is x-axis and again it is y-axis, it is the region 0. So here find the maximum value, 10 is your maximum value, then I'll write 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So now mark these points. A is 0, 5, 10 is 10, 0. 0, 5, this is 5, 0, 5 and 10, 0. Just join these points. And next is 0, 6, 8, 0. 0 to 6 and 8 to 0. Join these 2 points. Have joined 2 constraints line. So now, do we have any other points? No. So now, you just observe this. This region is feasible point because 2 constraints are connected each other. So here, you just find the first constraint and the second constraint. So first constraint is greater than or equal to 10. Greater than or equal to means it is above the region. It is opposite to region, and less than or equal to 24. Less than or equal to 24 means it is below the region. So first constraint is above the region. You just observe this. Here we have 2 constraints. This is first constraint and this is second constraint. First constraint is greater than or equal to 10. Greater than or equal to means it is opposite to this region. Opposite to this region means above the constraint, and less than or equal to second constraint is less than or equal to. Less than or equal to means it is below the region. So below the region and above the region means which area you need to shade. So you have to shade this area because it is a feasible region. So this is our feasible point. Connected point is this one. First constraint is greater than or equal to. Greater than or equal to means it is opposite to this region. This is the region point. Opposite to this region means this area above the constraint. And the second constraint is lesser than or equal to. Lesser than or equal to means it is towards the region. Towards the region means this area. So you have to merge both the areas. So you can use this as a feasible region. It is above the region and also we have below the region. So this area is called as feasible region. So now you can find the corner points here. The corner points are first corner point, second point and third corner point. We have 3 corner points. So first corner point is, I'll take it is A, then B and C. So first corner point is A of 0, 6 and B is 0, 5. 0, 5 and the C is 6, 2. 6, 2. So this is our corner points. I got 3 corner points A, B and C. A, B and C. Now you can find the minimum value. Why? Because the problem is minimization problem. So we have to find the minimum value. So how to find the minimum value? Again, you just write the objective function first. So objective function is minimization and the first corner point is 0, 6, 0, 6. Substitute the value of x and y. 200 into 0 plus 500 into 6. 0 plus 3000. So, and second corner point is 0, 5. 0, 5 and the third corner point is 6, 2. So, here substitute the value 200 into 0 plus 500 into 5. 2500. And the third point is 6, 2. 200 into 6 plus 500 into 2. 1200 plus 1000. It is 2200. So now you just observe these three values. So minimum value is 2200. It comes under the point called 6 and 2. So x is equal to 6 and y is equal to 2. So the minimum value is equal to 2200. It comes under the point x is equal to 6, y is equal to 2. So minimization set is equal to 2200 at point x is equal to 6 and y is equal to 2. So this is your minimization problem. So here you got a feasible region also, and after getting the feasible region you can find the minimum value using this corner points. So this is about minimization problem. And the next problem is maximize z is equal to 3x plus 9y. Again we have two different constraints here. So first convert it into standard form. X plus 3y is equal to 6. This is equation number 1. So put x is equal to 0, 3y is equal to 60 and y is equal to 20. So a of 0, 20. And put y is equal to 0, x is equal to 60. So b of 60, 0. And the second constraint, x plus y is equal to 10. Put x is equal to 0, y is equal to 10. So points are 0, 10. And put y is equal to 0, x is equal to 10. The point D is 10, 0. And also we have x less than or equal to y. So equation is x is equal to y. Put x is equal to 0, y is also equal to 0. So now we'll connect these points. This is x-axis and y-axis 0. So the maximum value is 60 is my maximum value here. So I will take 10, 20, 30, 40, 50 and 60. So scale is 10 centimeter. 1 unit is equal to 10 centimeter. The first point is 0, 20. So 0 to 20. First point is 0, 20. And the second point is 60, 0. 60 to 0. You just connect these 2 points now. And the next point is 0, 10, 10, 0. 0, 10 and 10, 0. I have connected these two regions. So now here I have x less than or equal to y. Put x is equal to 0, y is also equal to 0, right? So here I will mark 0, 0, 0, 0. Then I will join these 2 points now. You just observe this. Here I have actually 3 constraints. It is x less than or equal to y. You are not supposed to miss this constraint also. So I have marked 0, 0. You just connect this point. You just connect this point 0, 0. You can observe this now. You just observe this. Is there any feasible region? Yes, we have feasible region. So first constraint is less than or equal to 60. So here the first constraint is, this is first constraint and this is second constraint and this is third constraint. So first constraint is less than or equal to 0. Less than or equal to 0 means it is towards the region, right? It is towards the region. And second constraint is greater than or equal to 10. So this is my second constraint. Second constraint is greater than or equal to 10. Second constraint means above the region. Greater than means it is opposite to the region. Opposite means this area. And again I have less than or equal to y. Less than or equal to y means it is towards the region. So it is towards the region. So this is my feasible area. So this is called as feasible region in this solution. In this problem, we have this is a feasible solution. So these points are connected each other. So this is my feasible region. This is towards the region and this is also towards the region and this is above the region. This is above the region. So this is my feasible solution. So now I will shade this region. This is feasible region. So now find the corner points. So this is my corner points. This is corner point. This is corner point and again this is corner point. We have 4 corner points. So now what is the corner point here? A, B, C and D. So first corner point is 0, 10. 0, 10 and the second corner point is 0, 20 and third one we have it is 14, 12. 14, 12 and the fourth one we have, so fourth corner point is 5, 5. 5 and 5. So in graph sheet you can observe the point values and you can write the corner points. Using these corner points we can find the minimum value. So first point is 0, 10, 0, 10 and second point is 10, 0. Substitute the values here. 3 into 0 is 0, 10 into 9, 10 into 90, 90. And the second corner point 10 and 0. Substitute the values of x and y. 10 into 3 is 30. And the third one we have 14, 12, 14, 12 and 5 and 5. So 14 into 3 it is 42 plus 12 into 9 it is 108. So the total value is 150. So C value is 150 and again 5 into 3 15 plus 45 it is 60. So now you can find the minimum value out of this. Minimum value is 30. It comes under the points x is equal to 10, y is equal to 0. So here we have mixed objective function, minimization and maximization. I will find the minimum value. Min z is equal to 30. It comes under at x is equal to 10 and y is equal to 0. And maximum value is 150. So max z is equal to 150. It comes under x is equal to 14, y is equal to 12. So this is your solution for maximization and minimization. And the next problem is solve the following by graphical method. Again we have minimization problem. You just convert this into standard form. X plus y is equal to 8. Put x is equal to 0, y is equal to 8. So point A is 0, 8 and put y is equal to 0, x is equal to 8. Point B is 8, 0 and second equation is 3x plus 5y is equal to 15. So here we have different constraint greater than or equal to and less than or equal to. So put x is equal to 0, 5y is equal to 15, then y is equal to 3. So point C is 0, 3 and put y is equal to 0, 3x is equal to 15, x is equal to 5. Then D is 5, 0. We have two constraints. We got the value of A, B, C, D point. Just draw the graph now. X axis and y axis and region 0. So first point, so which is the highest? So now first see the highest value, maximum value is 8. So I will take 1, 2, 3, 4, 5, 6, 7, 8. So now first point is 0, 8, 8, 0. 0, 0, 8 and 8, 0. You just join these 2 points now. And second point 0, 3, 5, 0. 0 to 3 and 5, 0. Connect these 2 points. So this is minimization problem, and also we have different constraints. So one is greater than or equal to and less than or equal to. So first constraint is greater than or equal to. So this is greater than or equal to first constraint, and this is second constraint. Greater than or equal to means it is opposite to the region. So this is opposite to this region, this side above the constraint, and less than or equal to. Less than or equal to means towards the region. So towards the region means this position. So towards the region and above the region, we don't have any common point, right? So because of that, we can say it is not a feasible solution. So it is not having any feasible solution. So this problem is not having feasible solution because there is no common point connected to each other. It is above the constraint, there is no common point, and below the constraint, there is no common point. So there is no feasible solution. Finally, you have to write that the problem is having no feasible region and no feasible solution. The problem is having no feasible region and no feasible solution. So here we got 3 corner points because it is above the constraint means this area is my feasible region. So here I got 3 corner points. So first corner point is A and B, and I will make it as C. So first corner point is A of 0, 2, and the second corner point is 3, 0. Third one we have 1.3. 1.3, 0.5. 0.5. This is 0.5 and this is 1.3. So this area is common points. Here we got 3 common points. So now we'll find the minimum value. So minimize z is equal to 3x plus 5y. So first point is 0, 2, 3.0 and 1.3, 0.5. 0, 2, 3, 0, and third one is 1.3, 0.5. We'll find the minimum value here. So substitute the value. 3 into 0 is 0 plus 5 into 2. So it is 10. And 3 into 3, 9 plus 5 into 0 is 0. So answer is 9. And 3 into 1.3 plus 5 into 0.5. 3 into 1.3 is 3.9 and 5 into 0.5 and 5 into 0.5 is 2.5. Then add these two numbers, add these two values, so you will get 6.4. So here out of these 3 values, the minimum value is 6.4. It comes under the value x is equal to 1.3, y is equal to 0.5. So min z is equal to 6.4 at x is equal to 1.3 and y is equal to 0.5. So this is your minimum value to this solution. So this is about your unbounded solution and minimization problem. So this is about your special cases in LPP by graphical method. In my next session, I will explain some more problems. Thank you.